Welcome to the second part of Lecture 2 for Chem 418 on nuclear properties. In the second part of the lecture on nuclear properties, we're going to introduce nuclear models, primarily the liquid drop model, and we're going to show where it works, where it doesn't work, and where it fails is actually used to derive the idea of magic numbers. We're going to talk about nuclear stability from mass change using the nuclear mass parabola. We're also going to demonstrate how nuclei have shape and how this shape is measured. And then we're going to end the lecture on nuclear properties discussing spin, parity, and magnetic moments. Based on everything we've discussed, masses, how those masses can be used to evaluate binding energy, we can now use this information to actually develop a simple model of the nucleus. So we're going to talk about a model of the nucleus, and this model is basically going to be based on a liquid drop. Very simple. We're going to call it the liquid drop model of the nucleus. That's what it's called. And some of the concepts of this model are described here. So that the volume of nuclei are basically based on the number of nucleons present. You can't compress nuclear matter, so the size is fundamentally based on the number of nucleons. This is the basis of the equation of the nuclear radius. Radius is just proportional to the number of nucleons. And something being incompressible sounds like water. And the total binding energy of nuclei are nearly proportional to the number of nucleons present. So there's a saturation character. That means that the nucleons tend to only interact with a small number of other nucleons. So if we thought of water, water only tends to interact with other water around it. So it seems to be a reasonable model. Nucleons that are saturated, that have other nucleons around it, will have a different characteristic than those on the surface, because the surface nucleons don't have other nucleons around it at the surface. So we'll need to consider that term. All these together is the basis of the liquid drop model. It considers the number of protons and neutrons in a nucleus, how they may arrange, interact, and if we're also going to talk about a nuclear drop model, the liquid drop model of the nucleus, we tend to think spherical. And this is all developed from mass data, and you can get some information from this web link here. And fundamentally, what this describes is that nucleons are going to have different interactions if they're in the volume, right? If they're in the middle of this drop, they're saturated. If they're on the surface, well, they're not completely saturated. They've got some interactions here, but nothing out over here. There's a Coulombic interaction. The reds are protons, the whites are neutrons. So there's a force interaction, which is going to tend to spread the protons out. There's an asymmetry interaction. The neutrons, protons want to pair up fundamentally. And then if there's something left over, that's an asymmetric term. And then there's pairing of the nucleons themselves. So neutron, neutron, proton, proton pairs. So there's a few different terms that try to expand this model beyond just a simple liquid drop. On the previous slide, we showed the physical representation. Now let's talk about the mathematical representation. Equation here, where I'm going to calculate the binding energy as a function of different terms. And each one of these terms represents an example of what we provided in the previous slide on the discussion of where that nucleon is living in the nucleus. So this first term, this is a volume term. It's the dominant term in the liquid drop model. And at first approximation, the binding energy is proportional to the total number of nucleons. So I've got a term here that describes the total number of nucleons. This term here, the n minus z squared divided by a, represents a symmetry energy term. The binding is due to nuclear forces. That's due to nuclear forces is greatest for a nucleus with the equal number of neutrons and protons. It's kind of a pairing aspect, the pairing of neutrons and protons. This is just something that comes out of some of the studies. So they want to try to work this term into a volume term. So this is why the equation has these relationships between neutrons, protons, and A. And then there's some constants that are used to evaluate the term. The second term, that's our surface term. See, and it's shown here, subscript 2. Remember, there were constants for that, and then I've got another constant for the K. And then, again, N, Z, and A are my other terms. And since this is a surface term, it's subtracting from the energy. Remember that nucleons at the surface are unsaturated. This surface term decreases with importance as the nuclear size increases. More nucleons are interfacing with the first term as opposed to the second term in relative terms. The third and fourth terms, those are Coulomb energy terms. The third term represents an electrostatic energy that comes from Coulomb repulsion. So it just talks about the number of protons. A is how those protons are fundamentally diluted. It's 8 to the 1/3, so it's a radius term. And all this says is that I've got some term, the number of protons increases this Coulomb energy, and this Coulomb energy takes away the energy from the binding energy, so it's a negative. The fourth term represents a correction term for charge distribution within a diffuse boundary. Okay, so then now this is bringing in a recognition that the boundary of the nucleus isn't a sheer drop-off, that you get nucleon density changes close to the edge of the nucleus. And then the final term, you see that's our fourth term that we were talking about, the Coulomb. And then the final term is a pairing energy term. And this takes in account some of the trends that are seen, that the binding energies for a given A will depend upon whether the N and Z are even or odd. If it's an even nucleus, they tend to be the most stable. So this is a term that's used. And two like particles tend to complete an energy level by pairing in opposite spins. So neutron and proton pairs, that's where some of that pairing information comes in. So again, it's kind of a correction. It's a little bit more complex than drops of water, but it is taking data that was measured for the binding energies, which again come from the masses for isotopes, and applying them to this model. Using the data that we've described to calculate the binding energy from the liquid drop model, one can compare experimental data to some of the calculations. Now, if we can get the binding energy, then we can get the mass. So what's shown here is an example of a comparison of experimental and masses measured through the liquid drop formula. So these are the differences, and the differences are listed in MeV, and we have it plotted against proton number and here against neutron number. And if you look at this, there's some trends. We see that at 2, 8, 20, 28, 50, 82, and 126 for both the neutrons and the protons, we see these variations. And this is kind of evidence that there's some stability going on at these numbers. So we get unusual stability exhibited with 2, 8, 20, 28, 50, 82, 126. We're going to see that these are magic numbers. These are numbers where nucleons, when they fill to those levels, both protons and neutrons, incur stability within the nucleus. You can think about it in terms of electrons. When you fill a shell in an electron, you get noble gases. The nucleons, we're going to learn, do the same thing. So neutrons and protons fill shells in nuclei, and we get these stabilities at these numbers. So this evidence is coming from mass. We're getting the binding energies, and then we also get some information related to elemental and isotopic abundances. This is deriving the fact that just like electrons, there's concept of closed shells in nuclei. So we're seeing a similarity, trying to identify some trends. Now, we've been able to use the liquid drop model, and if you look at the data, you see that there's differences up to on the order of 10 MeV, which isn't really good, But there's some areas where the description between the experiment and the modeling with the liquid drop model is pretty good. But these peaks, they're demonstrating the limits of the liquid drop model. And it also demonstrates the limits of the concepts that go into the liquid drop model, where we're modeling the nucleus as a drop of liquid, and it has limitations. We see that there's structure, we see that there seems to be shell effects. And if you can think about this, this is similar to even how the atom, the idea of the atom, evolved over times. So this liquid drop model, we got some information. It's bringing us to the point that we have magic numbers, and this is going to be used, and we'll discuss this later in the course, about nuclear structure and models that are related to shell properties. We'll call that the shell model. Another way of evaluating trends within nuclei is to look at something called mass parabolas. It's a way of demonstrating stability by constructing some binding energies. So what we have here is basically a way of showing how much extra energy a isotope has compared to the other isotopes in its isobar. So here we plot A of 157, A of 75, and fundamentally here we have energies. These are your Q values. So zinc 75 decaying to gallium 75 has this much energy, gallium to germanium, germanium to arsenic, and we see that there's a stability point here at arsenic. Krypton decays to bromine, bromine to selenium, and then the selenium to arsenic. If we go to the 157, we're looking at the lanthanides, we see a similar trends. So what this shows is it's a way of plotting the energy from one isotope to another. It also clearly identifies those stable isotopes. Those are at the bottom of the mass parabola. And for odd A isotopes, there's only one beta stable. And for even A isotopes, sometimes there'll be multiple beta stable isotopes. Previous slides show an example of the A157. Here's an example of the A156 mass parabola. This is taken from the table of the isotopes. What we want to show here is that there are two stable nuclei within this trend. And again, we see this mass parabola is going to give a lot more information. We see the beta decay here. So neodymium, promethium, samarium, europium, gadolinium. We're going up in Z, and then here we're going down in Z from tantalum all the way to gadolinium. But what we see is that as we go from the beta decay side, we're going to reach a point where this europium decays to the gadolinium stable, and then on this beta positive side, we go down and we hit a point where the homium would decay to dysprosium. Now dysprosium is at lower energy, so this is a plot, you can think of this as a plot of N for a given Z versus energy. Dysprosium here is lower than the holmium and the terbium. Now, the dysprosium is higher than the gadolinium, so there is a possibility that the dysprosium could decay to the gadolinium. Some isotopes do that through double beta decay, but the dysprosium isn't going to decay to the terbium because that's energetically not allowed, but the terbium here could still electron capture to gadolinium. So for an A of 156, we'd expect to see two stable isotopes, the dysprosium and the gadolinium. And the other thing you should note with this, for a mass parabola with two stable isotopes, you will not see the two stable isotopes right next to each other in N. So you wouldn't have stable terbium and stable gadolinium. They'd both have to be at the exact same energy level. The stable isotopes are usually off by 1 N. Right, let's further our discussion on nuclear shape. We brought this up a little bit earlier when we talked about the non-compressibility of nuclei in the liquid drop model, but there's an equation for nuclear radii that's shown here. And all it is that the you're basically stating that volumes are nearly proportional to the nuclear mass because the nuclei all have about the same density. You're filling up something with more and more nuclei, it's going to expand. What it actually turns out is that nuclei are not densely packed with nucleons, that packing varies, so the density is going to vary. So we have an equation that talks about the radii, and it's pretty simple. There's a constant times a to the 1/3. So as I add more neutrons and protons, the radii is going to increase. But what it increases by, this term R naught, can vary 1.1 to 1.6 femtometers for the equation above. So that variation has to do with the areas and type of isotopes that are examined. So this variations in nuclear radii can mean a few different things, has different implications. That there's a nuclear force field, that there's distribution in charges, and that there's nuclear mass distributions. So in other words, we're trying to get some of the information that we've talked about in terms of density, in terms of masses, and use that to get an idea of the shape of the nucleus. So right now we're just looking at something very simple, the radii, and we see that there's variations. We know that it will increase the more nucleons that are added, but how it increases varies somewhat. So here's a good question. How does one actually measure the radius of a nucleus? And what one can do is basically try to impinge upon that nucleus with another projectile. So it would be good to use a projectile that has a charge with it. And what one can do is evaluate a closest approach of that particle to the nucleus. So that's what we really want to do. We want to evaluate this term, the closest approach. And I have a few ways of evaluating this. Imagine that I take a projectile, have it accelerate towards the nucleus, and it gets bent, right? I get some scattering. How does that scattering from the nucleus indicate its distance? Well, I've got some d distance from the center of closest approach. And let's say I'm going to take an alpha particle. I've got some the particle's kinetic energy after the interaction, the particle's kinetic energy before the interaction. And what I can do for this distance, I actually want to get the distance of closest approach, which is head-on, and it's a collision. So when the particle's kinetic energy afterwards is equal to 0. So experiments are performed with this, and the most, the gold foil scattering experiment is the classic. But these experiments, what one can do is get the distance of closest approach. With a alpha particle, it's 2z, the charge, electron charge, divided by the kinetic energy. So you get distances of 10 to 20 femtometers for copper and 30 to 60 femtometers for uranium. Why are those differences, in the distances? They're pretty significant. It really has to do with the energy of the particle one is using to probe the nucleus. And what you're really looking at is Coulombic properties. So it's a close approximation, but it gives us ideas on what this distance of closest approach to the nucleus, and I can use that to get an idea of the radius of the nucleus. So I'm basically talking about a charge field that describes this scattering. And eventually I want to get, this is my impact parameter. I just want to understand the distance of closest approach, how the particle behaves when it gets scattered back. In the previous slide, we talked about an alpha particle impinging on a nucleus. Basically, any positively charged particle can be used to probe the distance. I could even use electrons, so I could use a negatively charged particle, but nuclear attractive forces become significant relative to the Coulombic forces. The closer you get, the more these nuclear attractive forces will start to override Coulombic repulsive forces. Neutrons can be used, but they're going to require higher energies because they're not subject to Coulombic forces. The high energies are needed for the de Broglie wavelength, so the wavelength that the neutron takes as it's traveling needs to be small compared to nuclear dimensions. And the problem with that, with using neutrons, is the higher the energy of the neutron, the less probable the interaction that neutron is going to have with the nucleus. So the cross-section, which we'll describe later, the cross-section, we talked about it in terms of the chart of the nuclides information, the probability of a reaction of a neutron with the nucleus to obtain this measurement is small. So really, measuring nuclei is best done with positively charged particles. As we alluded to on the previous slide, electrons can also be used for determining information about the nucleus. At moderate energies, data is fundamentally comparable to nuclei being spheres and uniformly charged. At high energies, more information comes out that shows that the nucleus has properties that indicates that it's no longer uniformly charged spheres. An example of that data is shown here, the reference provided here. And what this shows is scattering of electrons. One would assume from a Rutherford type cross-section, a Mott, which was earlier work, cross-section. And then this data, a Hofstadter data, shows that the cross-sections are lower and indicates structure of the nucleus. So in other words, data was obtained, information was used from previous studies and previous models that explain the nucleus. Now to explain this data, you start to bring in information related to nuclear structure that shows variations. One of the things that can be seen with electrons is that the radii are distinctly smaller than other methods. There seems to be a half density and a skin thickness associated with nuclei. So in other words, the half density is where the radius goes from full density at the core to half that core density. And then there's a skin thickness which defines the drop of density from 90% to 10%. The scattering data that was collected showed some differences in expected behavior of the nuclei, and that in turn led to the ability to describe the potentials in which the nucleus was constructed of. So in other words, the scattering experiments provided information, just like as we did with the liquid drop model. You had some models, you got some more data, you saw variations, so then you kind of change your models so that it helps explain the data that you're collecting better. So you see that it's an iterative process which was used often. It's used in all areas of science, but the examples we're talking about today relate to nuclear properties. So the scattering experiments, the data potentially approximately agreed with the square well potential in the nucleus. So imagine that the nucleons sit in this square well potential, this solid line that's shown here. This is for protons. You have a little bit of potential on the top here. This is for neutrons. There is no potential here. What this means is that neutrons can easily enter the potential, where protons have to have a bit of energy to get into the potential. This has to do with charge, so it takes coulombs and Coulomb property into the variation. Now, the data actually seems to point to a Wood-Saxon fit. And this is the dashed lines. And the difference is you see that the square wells, it's a little bit, the distance here is a little bit smaller at the bottom of the potential, larger at the top of the potential. But the reason that you have this is that this Wood-Saxon potential can describe some of the variations in nuclear density as a function of distance from the center of the nucleus. And you can determine something about a potential by understanding the potential at the origin and applying this equation where r is the distance. R is the distance here from the center from which you get a half potential. A is a constant, and this is the potential at the center of the nucleus. So now this information was utilized. You get an R naught of 1.35 to 1.6 femtometers for a square well. This term changes a little bit for the Wood-Saxon potential if you're looking at the half potential, so where it drops from the center to the half, or this where it goes from 90 to 10% of the full potential. This R naught goes to 2.2 femtometers. And this 90 to 10% drop can be defined as the nuclear skin thickness. Here's an example of the nuclear skin thickness. Pictorial example, you can imagine it that in the center you have a very dense nucleus. As you go out towards the edge of the nucleus, the nucleon density decreases, so you get this skin. And here's an example of the density at a given distance is equal to expanded equation, where it's a function of the initial potential, meaning the initial density. You see we have this distance here, which describes this skin thickness. You can use it to start assessing different properties of nucleons, and an example, what's shown here, is what percentage of nucleons in a given nucleus are in this skin. And we see that for something that's small, like carbon-12, the bulk of the nucleons are in the skin, whereas something for heavy, like uranium-238, the majority of the nucleons are outside of the skin. So again, we're seeing some variations in some nuclear properties, and all this comes back to just utilizing information that could be easily measured, such as mass and how it's applied. All right, we're going to complete lecture 2 by reviewing some properties that you may already be familiar with of the nucleus. And one is spin. We know that nuclei possess angular momenta that can be described through this term, where I is an integer or half integral number. That's where your nuclear spin comes in. You've used this at NMR. We want things with spin 1/2. Electrons generally distinguish between electron spin and orbital angular momentum. So again, what you may have learned about electron spin has correlations with neutron and proton spin. Like electrons and neutrons and protons have spin of 1/2, so it's a fundamental property. The nucleons in the nucleus contribute to the orbital angular momentum and the nuclear spins in a nucleus. So basically, what we're going to learn when we talk about the shell model is that the spin of a nucleus is determined by the unpaired nucleons. So if I have an even number of protons and an even number of neutrons, there's no spin. That's why on the chart of the nuclides, anything that's an even doesn't have that spin information, because it's assumed to be 0+. Protons and neutrons we're going to see that they're going to fill shells in the shell model, just like electrons. They're going to have orbital angular momentum, just like electrons, except, we're going to go to G, H's, and I's. So they're going to be a little bit different than electrons. And we're going to see some trends. Even A nuclei tend to have 0 or integral spins, and the odd A nucleus tends to have a half integral spin. For an odd A nucleus, that the unpaired nucleon, either a proton or a neutron, is going to be responsible for the spin of the entire nucleus. All even nuclei are 0 in the ground state, 0 spin. Nuclei with non-zero angular momenta also have magnetic moments, and these are from the spins of the protons and the neutrons. From nuclear magnetic resonance, you're familiar with the terms of the magneton, so it's basically the strength of this magnetic moment. These measured magnetic moments tend to differ from calculated values, and again, that indicates that protons and neutrons are not simple structures. So again, we're seeing this trend. You do a calculation, you measure something, they don't agree, come up with a reason that they don't agree. Another term that you likely have seen elsewhere is parity. We talk about a nucleus with a given spin and parity. It's really discussing a system and if there's a sign change in the space coordinates of that system. If I take a system, describe it as a wave, perform a parity operation on that wave. If the wave functions the same, it's even parity.
If the sign of that wave function changes, then it's odd parity.
You can think of parity as another term to describe the behavior in quantum mechanical state of the system that you're exploring. Parity has to be conserved, so there are certain trends where even and odd parity go to odd, even and even are even, odd and odd go to even. And what this really means is, if I talk about states, and we'll discuss this, as a nucleus decays and goes from one state to another, spin is important and parity is important. So as it slides into a spin state, does that spin state have a similar parity or not to the state that it's coming from?
We will see that more favorable transitions occur between low spin changes and no parity changes.
Parity is also connected with your angular momentum quantum number. States with an even angular momentum have even parity, so S, D states, where states with an odd angular momentum have an odd parity. P states, for instance, are odd numbers. They will have odd parities. We'll utilize this when we discuss the shell model.
And what we'll see in the shell model is that the orbital in which the nucleon resides is responsible for its parity, and it'll define its spin also. So for instance, we'll see that an unpaired nucleon can occupy the F 5/2 orbital. The spin would be 5/2. F is 3, it's an odd number, so the parity is odd. D 5/2 can also be occupied. D would give it a spin of 5/2, but D being an even number, as shown here, would give the parity an even orientation. So that orbital would be 5/2 plus.
And as a review, here are some properties of elementary particles: charges, rest mass, spins, magnetic moments, and if it behaves in what sort of statistics they follow. And we've talked about electron, photon, positron, neutron, and then proton within this lecture.
In the lecture on nuclear properties, we explored the use of nuclear data tools and provided examples on how they can be utilized. We discussed nucleon number, particularly the number of protons and neutrons in a nucleus, and how that relates to nuclear stability. We explored the role of nuclear mass in reactions, and we talked about the mass defect to determine energetics. We also explored binding energies, the mass parabola, and an introductory nuclear model based upon a liquid drop. This lesson also explored how to determine Q values in a number of different routes, including calculations, finding the data for specific reactions, or calculating specific reactions from the Q value calculator. We discussed how nuclear radii are determined. We talked about nuclear potentials and models, and also briefly discussed nucleon distribution within the nucleus, how nuclear matter density changes as one travels from the center to the edge of a nucleus. We also explored some quantum mechanical terms, and this is fundamentally a review, terms you should have seen previously.
Here's an example of some questions you should be able to answer after this lecture. What is binding energy? Well, it's just the difference between the constituents that make up the isotope and the mass of the isotope itself. The total binding energy is shown here, where I take the number of protons, that mass, add it to the mass of the number of neutrons, and subtract the actual mass of that isotope. The binding energy is positive, and this binding energy can represent the change of that mass that goes into some energy that keeps the nucleus together. What does this binding energy predict? Well, it predicts a few things. One, that if I look at binding energy as a function of mass number, we get this binding energy curve. We see that there are some properties to this curve. As I go up to about from A of 1 to 56, I keep increasing. So this means if I take elements and put them together, I can fuse elements and gain energy. When I get to this iron group, this peak iron group here, I have a maximum value, and this is one of the reasons that iron has a relatively high abundance compared to other elements. So the iron group, that elemental abundance, is related to this nuclear property. And then finally, I can fission an isotope, something that's heavier. I can go from something heavy to something lighter. The binding energy increases, so energy gets released. Another question could be relationship between stable isotopes and the number of neutrons and protons. Well, we discussed that of the stable isotopes, over half of them are even. About an equal number are even-odd, odd-even. And there are only 4 stable isotopes with odd number of neutrons and odd number of protons. So even nuclei tend to be the most stable. What is the Q value? Well, for nuclear reactions, the Q is just the energy of the reaction. So it's difference between, basically you can say it's the mass difference between the parent and the daughter. And that mass difference, if you measure it in atomic mass units, you can convert it to MeV by multiplying the atomic mass unit by 931.5 MeV per AMU. But this really comes from E equals mc squared. How can one find the Q value for a reaction or decay? We'll use the mass excess to set up the equation. So a parent minus the daughter using the mass excess. You can use the Q value calculator from the web, and we showed that. Or I can, depending if it's just a simple decay reaction, the data might be available in something like the table of the isotopes. How can radius be measured? Generally by scattering of charged particles. One could use both positively and negatively charged particles, electrons, protons, alpha particles. And they will give information about the scattering, and then that scattering information can be utilized to not only provide information on the radius of the nucleus, but give some details on the structure of the nucleus itself. What are some properties of the nucleus that can be measured? Well, we measured mass properties, but we can also measure nuclear spin, we can measure parity, and we can measure magnetic moment. And all these are windows that help us explain the properties of the nucleus.
When you have completed Lecture 2, please comment on the blog and respond to the Lecture 2 quiz. In summary, Lecture 2 provided a strong overview of the tools used for nuclear data. This included the nuclear wallet card, the isotope browser, and 2 Q-value calculators. One from Brookhaven was reviewed in detail. The important concepts that you should take away from this lecture include that the number of neutrons and protons in a nucleus influences their stability, that the nuclear mass can be used for identifying trends, such as energetics, the Q value, and the binding energy, that the binding energy is related to important reactions, such as fission, fusion, and that nuclear radii and skin thickness can be measured and calculated. This lecture also discussed the basic concepts of the liquid drop model, which, as shown here, details that you should be familiar with include what the terms in the equations represent, the relationship to magic numbers, and magic numbers will be discussed in more detail later in the course. This lecture introduced spin and parity, terms that you should have seen before. Anyone who's done nuclear magnetic resonance, NMR, has already worked with nuclear spin. We'll see that spin and parity are important terms in radioactive decay. For alpha, beta, and gamma decay, spin and parity changes will be shown to be important. We'll discuss this later in the course. There was some basic information on nuclear magnetic moments and measurement of nuclear radii. You should be familiar with the very fundamental basics of this. And then there was a brief discussion on nuclear potentials, the Wood-Saxon potential, for example, and this will be discussed in more detail later in the course when lectures on nuclear models are presented.
Bye.